before the first sound is ever heard, before thunder rolls across the sky or rain touches the ground, lightning is already there. It is born in silence, hidden inside towering clouds that look calm from a distance but are, in truth, among the most violent environments on Earth. To stand beneath a storm is to stand beneath a living engine of energy, pressure, heat, and motion. Lightning is not just a flash of light. It is a moment when the sky itself breaks open. For as long as humans have existed, lightning has inspired awe, fear, and reverence. Ancient civilizations saw it as the weapon of gods. Zeus hurled it from Olympus. Thor carried it in his hammer. In many cultures, lightning was a sign of divine anger or divine protection, a message from the heavens written in fire. Even today, despite satellites and sensors and supercomputers, lightning still holds a sense of mystery. It arrives without warning, lasts less than a second, and yet releases more power than many human-made explosions. At its core, lightning is electricity on a planetary scale, but understanding how it forms requires stepping into the heart of a thunderstorm, into a place where air rises at astonishing speeds and water exists in multiple states at once. Inside a storm cloud, warm air surges upward from the ground, carrying moisture high into the atmosphere. As it rises, it cools, forming tiny droplets of water, ice crystals, and soft pellets of ice known as graupel. These particles collide again and again, driven by powerful updrafts that can exceed speeds of 100 miles per hour. Each collision transfers electrical charge. For reasons scientists are still refining, lighter ice crystals tend to become positively charged and are carried upward, while heavier graupel becomes negatively charged and sinks toward the lower part of the cloud. Over time, the cloud becomes electrically layered, like a giant battery floating in the sky. The top grows increasingly positive, the bottom grows increasingly negative, and between them, tension builds. The air between these charged regions resists the flow of electricity. Under normal conditions, air is an excellent insulator, but as the electrical difference grows stronger, the resistance weakens. Invisible pathways of ionized air begin to form, branching downward from the cloud in faint, step-like movements called stepped leaders. These leaders are too dim for the human eye to see clearly, but they are searching, probing the air below for a connection. At the same time, the ground beneath the storm responds. The negative charge overhead repels electrons in the surface of the Earth, pushing them deeper into the ground and leaving behind a positively charged surface. Trees, buildings, rocks, and even people become part of this electrical landscape. From tall objects, invisible streamers of positive charge rise upward, reaching toward the descending leaders from the cloud. When a leader and a streamer connect, the circuit is completed. In that instant, an immense surge of electricity races along the newly formed channel. This is the return stroke, the brilliant flash we recognize as lightning. It travels upward from the ground to the cloud at a speed approaching 1/3 the speed of light. The channel heats to temperatures hotter than the surface of the sun, reaching nearly 50,000 degrees Fahrenheit in a fraction of a second. The air around the lightning channel expands violently under this extreme heat, creating a shockwave that we hear as thunder. Thunder is not a single sound, but a complex rolling echo shaped by the landscape, the atmosphere, and the path of the lightning itself. Close strikes crack and snap with explosive force. Distant strikes rumble like drums across the sky. Yet lightning does not always strike the ground. In fact, most lightning occurs entirely within clouds or between neighboring clouds. These intracloud flashes illuminate the sky from within, turning clouds into glowing cathedrals of light. Sheet lightning, often seen on distant horizons, is simply intracloud lightning reflected across vast cloud surfaces. It can flicker silently for minutes, a distant reminder of storms beyond sight. For centuries, lightning was uncontrollable and unpredictable. But in the 18th century, a single experiment changed humanity's relationship with the storm. Benjamin Franklin's famous kite experiment, dangerous as it was, proved that lightning was electrical in nature. From that moment forward, lightning was no longer only myth. It became a subject of science. The invention of the lightning rod transformed cities. By providing a safe path for electrical discharge, lightning rods protected buildings, ships, and later entire power grids. They did not prevent lightning, but they guided it, redirecting destruction into controlled release. This simple idea saved countless lives and reshaped architecture across the world. Despite these advances, lightning remains one of nature's most deadly forces. Every year, it kills thousands of people worldwide and injures many more. It ignites wildfires, damages infrastructure, and disrupts aviation. A single strike can shatter concrete, split trees, and vaporize metal. And yet, the odds of being struck are low enough that many underestimate the risk, forgetting that lightning does not need to hit directly to be fatal. Ground currents inside flashes can carry lethal energy far from the strike point. Lightning is also deeply connected to life itself. Long before humans existed, lightning may have helped spark the very chemistry that led to life on Earth. Early experiments showed that electrical discharges passing through mixtures of gases could produce amino acids, the building blocks of proteins. In this way, lightning may have played a role not only in shaping the planet's surface, but in shaping biology itself. As storms move across continents and oceans, lightning traces invisible patterns of energy exchange between Earth and sky. At any given moment, thousands of storms are active around the world, producing millions of lightning strikes each day. From space, satellites capture this constant flickering, a nervous system of light pulsing across the planet. And yet, for all its familiarity, lightning still holds secrets. Scientists continue to study why some storms produce far more lightning than others, why certain flashes branch wildly while others follow straight paths, and why lightning sometimes strikes far from the storm that created it. Each answer reveals new questions, deeper layers of complexity hidden within a flash that lasts less than a heartbeat. This is only the beginning, because lightning is not one phenomenon but many. It comes in colors beyond white. It moves upward as well as down. It reaches into space. It appears where no storm seems present. And in the chapters ahead, we will follow lightning deeper into rare forms, extreme environments, human encounters, and the future of storm science itself. Lightning is not a single event. It is a process, one that begins long before the flash ever touches the ground. High above the surface of the Earth, inside towering thunderclouds that can stretch higher than Mount Everest, invisible forces begin to organize themselves. Warm air rises, carrying moisture upward. As it climbs, the air cools and water droplets freeze into ice crystals. These particles collide again and again, driven by powerful updrafts that can exceed 100 miles per hour. Each collision transfers tiny electrical charges, separating positive from negative, slowly turning the cloud into a massive, floating battery. Over time, a strange imbalance forms. The top of the storm cloud becomes positively charged, while the lower regions grow heavily negative. Below, the ground responds. Trees, buildings, open fields, even human bodies quietly accumulate positive charge, drawn upward by the electric tension overhead. The atmosphere itself becomes a stretched wire, waiting to snap. What we perceive as calm is often only the final breath before release. Lightning does not strike suddenly, it searches. Before the brilliant flash, a faint, invisible path descends from the cloud in steps, each one probing the air ahead. Scientists call this a stepped leader, a branching, jagged tendril of negative charge that moves toward the Earth in rapid bursts, pausing briefly between each advance. It is silent, unseen, and faster than any living thing can react. At the same time, from the ground, thin streams of positive charge rise upward, reaching for the descending leader. When one of these invisible fingers connects, the circuit is complete. Only then does lightning truly exist. The return stroke races upward along the newly formed channel at nearly the speed of light, heating the air to temperatures hotter than the surface of the sun, over 50,000 degrees Fahrenheit in a fraction of a second. The air explodes outward, expanding violently, creating the shockwave we know as thunder. Light and sound are born from the same event, but arrive at our senses separated by distance and time. That flash, which seems to last an instant, is often not just one strike, but many. Lightning can pulse along the same path multiple times in rapid succession, giving it the flickering appearance we sometimes notice in slow-motion footage. Each pulse reinforces the channel, carving a temporary scar through the atmosphere that fades within seconds. And yet, despite its destructive reputation, lightning is not random chaos. It follows patterns, it obeys rules, it prefers tall, isolated objects, but not always the tallest. It can strike the same place repeatedly. Some structures are hit dozens, even hundreds of times per year. Lightning does not seek targets, it completes circuits. Across the planet, lightning storms follow rhythms shaped by geography and climate. Equatorial regions experience near-constant electrical activity, with thunderstorms blooming almost daily over warm landmasses. Central Africa, parts of South America, and Southeast Asia rank among the most lightning-active places on Earth. In contrast, polar regions remain largely quiet, their cold, stable air rarely giving rise to the violent convection needed to generate charge separation. But lightning does not belong only to Earth. Spacecraft have detected lightning on Jupiter, Saturn, Uranus, and Neptune, storms so massive they dwarf entire continents. On Jupiter, lightning bolts may be hundreds of times more powerful than those on Earth, illuminating cloud tops with blinding flashes that reveal the immense scale of alien weather systems. Even Venus, wrapped in dense clouds of sulfuric acid, shows signs of electrical activity, though its lightning behaves differently, shaped by a hostile atmosphere unlike anything humans could survive. Back on Earth, lightning plays a role far older than humanity itself. Long before humans learned to fear it, lightning shaped ecosystems. It ignited wildfires that cleared forests, recycled nutrients, and opened landscapes for new growth. Many plant species evolved to depend on fire triggered by lightning strikes. Some seeds only germinate after exposure to intense heat. In this way, lightning became an agent of renewal as much as destruction. Lightning also alters the chemistry of the air. Each strike breaks apart nitrogen molecules, allowing them to combine with oxygen and fall to the ground as nitrates, a natural fertilizer essential for plant growth. Before industrial agriculture, lightning was one of the primary ways nitrogen entered the soil in usable form. Every storm quietly fed the earth. Humans, however, have always viewed lightning through the lens of fear and meaning. Ancient cultures saw it as the voice of gods, the weapon of sky deities, a sign of judgment or favor. Zeus hurled lightning from Mount Olympus. Thor wielded it with his hammer. Indigenous cultures across continents interpreted lightning as spirit, messenger, or warning. Even today, despite scientific understanding, lightning retains an emotional power few natural phenomena can rival. Modern technology has not removed lightning from our lives. It has simply changed our relationship with it. Power grids, communication towers, aircraft, and cities have turned lightning into both a threat and a challenge. Airplanes are struck by lightning regularly, yet passengers rarely notice. The aircraft's skin safely channels the electricity around the cabin, releasing it back into the atmosphere. Buildings bristle with lightning rods and grounding systems, silently guiding energy away from vulnerable structures. Still, lightning remains unpredictable. Each year, thousands of people around the world are injured or killed by lightning strikes. Many incidents occur under clear skies, miles from the storm that produced the bolt. Lightning can travel horizontally through clouds, emerging unexpectedly far from rain or thunder. The phrase "bolt from the blue" is not poetic exaggeration, it is meteorological fact. There are even forms of lightning that defy expectations entirely. Some flashes travel upward instead of down, leaping from storm tops into the upper atmosphere. These phenomena, known as sprites, jets, and elves, occur high above thunderstorms, glowing red and blue for mere milliseconds. Invisible to the naked eye for most of human history, They were only confirmed in the late 20th century, revealing that lightning's reach extends far beyond the clouds we see. In recent years, scientists have begun to realize that lightning may also influence Earth's radiation belts, triggering waves that knock high-energy particles out of orbit. In this way, a storm over a forest or ocean can affect regions of space tens of thousands of miles above the planet. The boundary between weather and space is thinner than we once believed. As climate patterns shift, lightning itself may be changing. Warmer temperatures increase atmospheric moisture and instability, the raw ingredients of thunderstorms. Some studies suggest that lightning frequency could increase significantly in a warming world. More storms mean more fire, more damage, and more unpredictable interactions between nature and human infrastructure. Yet despite all our instruments, satellites, and models, lightning still resists complete understanding. No two bolts are ever identical. Each is shaped by countless variables: temperature gradients, humidity, wind shear, terrain, atmospheric chemistry. Every strike is a momentary signature of conditions that will never occur in exactly the same way again. Lightning is not simply a flash of light. It is the visible expression of tension between sky and ground, heat and cold, order and chaos. It is nature reminding us that the atmosphere is alive with energy, constantly moving, constantly balancing itself. And as storms gather on the horizon, as clouds darken and the air grows heavy, the stage is set once more. Somewhere within that towering sky, charges are separating, paths are forming, and the ancient conversation between earth and sky is about to speak again. As storms mature, lightning begins to reveal its true complexity. What most people see as a single flash is, in reality, a rapid sequence of electrical events unfolding in fractions of a second. The sky does not simply light up. It discharges, resets, and discharges again, following invisible pathways carved by electric fields long before the first visible spark appears. Inside a thundercloud, electricity organizes itself into layers. The upper regions of the cloud often carry a strong positive charge, while the middle and lower regions accumulate negative charge. This separation is not accidental. Rising ice crystals collide with falling hailstones and graupel, transferring electrons in a chaotic dance driven by turbulence and gravity. Over time, this imbalance grows so extreme that the atmosphere itself can no longer contain it. The air, normally an excellent insulator, begins to fail. Molecules stretch under the stress. Electrons tear free. And suddenly, a faint branching channel known as a stepped leader begins its descent toward the ground. This leader is invisible to the naked eye, moving in short, jagged steps, feeling its way through the air like a blind explorer. It searches for a connection, reaching downward in a series of rapid pauses, each step lasting only microseconds. At the surface of the Earth, objects respond. Trees, buildings, hills, even human bodies begin to send upward-reaching streamers of positive charge, drawn toward the approaching leader. This is the moment of choice. The lightning bolt does not simply strike the tallest object. It strikes the object that completes the electrical circuit most efficiently at that exact instant. When the two channels meet, the real lightning happens. A massive surge of current races upward along the established path at nearly the speed of light. This return stroke is what we see as the brilliant flash, heating the air to temperatures hotter than the surface of the sun, over 50,000 degrees Fahrenheit. The sudden expansion of this superheated air creates a shockwave that ripples outward, cracking the sky open with thunder. But the story does not end there. Many lightning strikes are not single events but rapid-fire sequences. The same channel can discharge multiple times, causing the flickering effect often seen during storms. Each pulse briefly re-illuminates the same path, giving lightning its signature trembling glow. What appears random is, in fact, a structured release of stored energy, carefully shaped by physics and chance. Some lightning never reaches the ground at all. Cloud-to-cloud lightning flashes between regions of opposite charge within the storm, illuminating towering anvils from within like colossal lanterns. Sheet lightning spreads horizontally, lighting entire skies without a visible bolt. And then there are the rare and mysterious forms, sprites, elves, and blue jets, brief luminous events that occur far above thunderstorms, reaching into the upper atmosphere. Sprites appear as glowing red tendrils stretching downward from the ionosphere, often triggered by powerful positive lightning strikes. Elves expand as rapidly growing rings of light at the edge of space, lasting only milliseconds. Blue jets erupt upward from the tops of thunderclouds, narrow cones of electric energy piercing the sky. For most of human history, these phenomena were dismissed as myths or optical illusions. Only with modern high-speed cameras did science finally confirm their existence. Lightning is not confined to Earth. On Jupiter, lightning bolts are thought to be far more powerful than anything seen on our planet, fueled by immense storms and a thick, turbulent atmosphere. Saturn's lightning crackles within clouds of ammonia and water ice, creating flashes that can be detected across the solar system. Even Venus shows signs of electrical activity, though its storms behave very differently beneath dense layers of carbon dioxide. This cosmic perspective reframes lightning not as an anomaly, but as a universal process, a natural consequence of energy-seeking balance in turbulent atmospheres. On Earth, lightning plays a critical ecological role. It fixes atmospheric nitrogen, converting it into compounds that fertilize soil and support plant growth. Long before industrial agriculture, lightning helped sustain ecosystems by enriching the land with nutrients essential for life. In this sense, storms are not just destructive forces, they are creators, quietly shaping the chemistry of the planet. Yet lightning remains deeply personal in its danger. Each year, thousands of people around the world are struck by lightning. Some survive with scars etched into their skin, intricate, fern-like patterns known as Lichtenberg figures, formed by electricity traveling across the surface of the body. Others experience neurological effects that alter memory, sensation, or personality. Lightning does not always kill, but when it touches the human nervous system, it leaves marks that are invisible as often as they are physical. Animals are equally vulnerable. Herds of cattle have been killed in single strikes, the current spreading through the ground beneath their hooves. Birds perched on power lines are usually safe because electricity follows the easiest path, but during storms, even these rules can break. Nature offers no guarantees. Despite centuries of observation, lightning still defies full prediction. Meteorologists can forecast conditions favorable for storms, but the precise moment and location of a strike remain elusive. Each bolt is shaped by microscopic variations in air density, humidity, and electric fields, variables too complex to fully model. And perhaps that uncertainty is part of lightning's enduring power over the human imagination. Ancient cultures saw lightning as divine judgment or celestial communication. Zeus hurled it as a weapon. Thor wielded it with his hammer. In many traditions, lightning marked the presence of gods, spirits, or cosmic authority. Even today, a powerful strike can silence a crowd, pulling eyes skyward in shared awe. Modern science has stripped lightning of its mysticism, but not its wonder. Knowing how it forms does not make it any less breathtaking. If anything, understanding its complexity deepens our respect for the forces at work above our heads. As storms move across the landscape, lightning traces invisible maps in the sky, temporary roads of energy that vanish as quickly as they appear. Each strike is unique, shaped by conditions that will never exist again in exactly the same way. No two bolts are identical. Each is a momentary fingerprint of chaos and order colliding. And while we watch from below, counting the seconds between flash and thunder, lightning continues its ancient work, balancing charges, shaping ecosystems, and reminding us that even in the age of satellites and supercomputers, nature still holds power beyond our control. In the next part, we will move closer to the human experience of lightning, how people have tried to understand it, tame it, protect themselves from it, and in some cases, harness its power. Because lightning does not exist only in the sky. It exists in our history, our technology, and our future. Lightning is often described as a strike from the sky, but that description barely scratches the surface of what truly happens during a thunderstorm. In reality, lightning is a complex conversation between clouds, air, and Earth itself, a rapid negotiation of energy that builds silently long before the first flash ever appears. By the time lightning reveals itself, the atmosphere has already been preparing the moment with astonishing precision. Inside a towering thundercloud, chaos begins to organize. Warm air rises from the ground, lifting moisture high into the sky where temperatures drop far below freezing. Tiny ice crystals and soft hailstones collide violently, pushed upward by powerful updrafts and dragged downward by gravity. With every collision, electrical charges separate. Lighter ice particles tend to become positively charged and are carried toward the top of the cloud, while heavier particles gather negative charge and sink toward the base. Over time, the cloud becomes electrically polarized, a massive floating battery charged with unimaginable energy. But the cloud does not exist in isolation. The negative charge gathering at its base begins to influence the ground below. Electrons on Earth's surface are repelled, pushing positive charges upward. Trees, buildings, mountains, and even people become subtly charged, forming invisible pathways stretching skyward. The air between cloud and ground, usually an excellent insulator, is now under extreme electrical stress. Every second that passes increases the tension. When lightning finally begins, it does not arrive as a single dramatic bolt. It starts quietly, invisibly, with a faint thread of ionized air called a stepped leader. This leader descends from the cloud in a jagged, searching pattern, advancing in small bursts toward the ground. It branches repeatedly, testing multiple paths at once, feeling for the route of least resistance. This entire process happens faster than the human eye can register, yet it determines where the lightning will strike with surgical precision. As the leader approaches the surface, something extraordinary happens. Objects on the ground respond. Upward streamers of positive charge leap skyward from trees, rooftops, and ridgelines, racing to meet the descending leader. The instant they connect, a conductive channel is completed, and the true lightning strike erupts. A powerful return stroke surges upward through the channel, carrying tens of thousands of amperes of current. This is the brilliant flash we see, bright enough to outshine the sun for a fraction of a second. The heat generated in that channel is almost impossible to comprehend. Temperatures can reach around 50,000 degrees Fahrenheit, hotter than the surface of the sun. The surrounding air expands explosively, creating a shockwave that ripples outward. Thunder is not a sound produced by lightning itself, but by the violent expansion and collapse of superheated air. Each crack, rumble, and rolling boom tells the story of distance, terrain, and the shape of the lightning channel twisting through the sky. Yet not all lightning strikes the ground. In fact, most lightning never does. The majority occurs within clouds or between neighboring clouds, flickering silently at high altitude. These intracloud and cloud-to-cloud discharges illuminate entire storm systems from within, turning thunderheads into glowing cathedrals of light. Pilots flying at night sometimes witness storms that appear to pulse from the inside, flashing repeatedly without a single bolt touching Earth. Even more mysterious are the forms of lightning that reach upward instead of downward. Sprites, jets, and elves are fleeting electrical phenomena that occur above thunderstorms, high in the mesosphere and lower ionosphere. Sprites resemble massive red jellyfish-shaped bursts, stretching tens of miles into space. Blue jets shoot upward like narrow beams from cloud tops. Elves appear as enormous expanding rings of light, lasting less than 1,000th of a second. For centuries, these phenomena went unrecorded, dismissed as myth or optical illusion, until modern cameras finally confirmed their existence. Lightning also behaves differently depending on geography. In tropical regions, Storms are frequent and intense, fueled by constant heat and moisture. Places like Central Africa, Northern South America, and Southeast Asia experience lightning almost daily during certain seasons. In contrast, dry regions may see fewer storms, but the lightning that does occur can be exceptionally dangerous, igniting wildfires that reshape entire landscapes. One of the most lightning-active places on Earth is Lake Maracaibo in Venezuela. Here, storms form with such regularity that lightning flashes hundreds of nights each year, sometimes at a rate of dozens of strikes per minute. This phenomenon, known as the Catatumbo lightning, has persisted for centuries and was even used by sailors as a natural lighthouse. Scientists believe the unique geography, warm lake waters, surrounding mountains, and steady atmospheric conditions creates the perfect environment for constant electrical storms. Lightning is not limited to Earth alone. Scientists have detected lightning on other planets, including Jupiter and Saturn, where storms dwarf anything seen on our world. On Jupiter, lightning bolts can be thousands of times more powerful than those on Earth, fueled by immense pressure and turbulent atmospheres. Even Venus shows signs of electrical activity, though its thick clouds and extreme conditions make direct observation difficult. Despite its destructive reputation, lightning plays a vital role in Earth's systems. Each strike helps convert nitrogen in the atmosphere into forms that plants can absorb, enriching soil naturally. Long before industrial fertilizers existed, lightning provided a crucial source of nitrogen for ecosystems worldwide. In this way, lightning acts as both destroyer and sustainer, burning forests while simultaneously feeding future growth. For humans, lightning has always inspired fear, reverence, and imagination. Ancient civilizations saw it as the weapon of gods Zeus, Thor, Indra, symbols of divine authority and power. Even today, lightning remains one of the few natural forces that can make modern technology feel fragile. Power grids fail. Electronics are damaged. Aircraft are designed to withstand strikes because avoiding them entirely is impossible. And yet, despite all we have learned, lightning still refuses to be fully tamed or predicted. Meteorologists can forecast storms, identify conditions favorable for lightning, and issue warnings, but the exact moment and location of a strike remain elusive. Each bolt is the result of countless variables aligning in a fraction of a second: temperature, moisture, particle collisions, electrical gradients, all interacting in a dynamic, ever-changing atmosphere. Standing beneath a storm, watching the sky fracture with light, it becomes clear why lightning has captivated humanity for as long as we have existed. It is energy made visible, a reminder that the air above us is alive, moving, charged, and powerful beyond our control. In every flash, the planet reveals a glimpse of its raw electrical heartbeat, sudden, brilliant, and unforgettable. As our journey through the world of lightning continues, we begin to understand that this phenomenon is not only a force of destruction, but also a powerful architect of the natural world. Long before humans learned to fear lightning, Earth itself depended on it. Billions of years ago, when the planet's atmosphere was young and unstable, lightning played a crucial role in shaping the chemistry of life. Electric discharges breaking through primitive skis helped convert simple gases into more complex molecules, including amino acids, the basic building blocks of life. In this way, lightning may have helped ignite biology itself, acting as a silent partner in the origin story of every living thing. Even today, lightning continues to shape ecosystems in subtle but profound ways. When lightning strikes dry landscapes, it can trigger wildfires, events that seem catastrophic, yet are often essential for renewal. Many forests rely on fire to clear old growth, release seeds, and recycle nutrients back into the soil. Certain plant species have evolved to survive lightning-triggered fires, their seeds sealed in protective shells that only heat can unlock. In this cycle, lightning becomes both destroyer and creator, ending one chapter of life while opening another. Lightning also influences the planet's nitrogen cycle. Every flash superheats the air around it to temperatures hotter than the surface of the sun. In that instant, nitrogen molecules split apart and recombine with oxygen, forming compounds that fall to the ground with rain. These compounds fertilize soil, feeding plants and supporting food chains across entire ecosystems. Without lightning, Earth's natural supply of usable nitrogen would be far weaker, and life as we know it would struggle to thrive. Yet lightning does not limit its reach to forests and plains. Over the oceans, massive thunderstorms crackle with electrical energy, their flashes illuminating towering clouds from within. These oceanic lightning storms help regulate atmospheric circulation, redistributing heat and moisture across the planet. Satellites watching from space see lightning as a pulse, a heartbeat of Earth's weather system, signaling where energy is rising, moving, and transforming. For humans, lightning has always existed at the edge between wonder and fear. Ancient civilizations saw lightning as the language of gods. Zeus hurled thunderbolts from the heavens. Thor's hammer shook the sky. In many cultures, lightning symbolized divine judgment, power, or revelation. Even today, standing beneath a darkened sky as thunder rolls overhead awakens something ancient within us, a reminder that we are small in the presence of nature's raw force. As science advanced, humans began to decode lightning's behavior. Benjamin Franklin's experiments revealed that lightning was electrical, not supernatural. From that moment, humanity's relationship with lightning began to change. We learned to protect buildings with lightning rods, to ground structures safely, to predict storms before they arrive. Yet, despite centuries of study, lightning still refuses to be fully controlled or predicted. Each strike remains unique, shaped by countless variables invisible to the human eye. Modern research has revealed that lightning is far more complex than a single bolt from cloud to ground. Inside storms, electrical charges dance in layered structures, with positive and negative regions shifting constantly. Lightning often begins invisibly, branching within clouds before ever touching Earth. Some discharges shoot upward into space, creating brief flashes known as sprites, jets, and elves, luminous events that last only milliseconds, glowing red or blue high above thunderclouds. These upper atmosphere lightning events remind us that storms connect Earth not only to the ground below, but to the edge of space itself. Lightning also challenges human technology. Aircraft are struck by lightning thousands of times each year, yet most passengers never notice. Engineers design planes to conduct electricity safely across their surfaces, allowing lightning to pass without harm. Power grids, communication networks, and satellites must all be built with lightning in mind. A single strike can travel through systems at the speed of light, overwhelming circuits and triggering cascading failures. In this way, lightning tests the resilience of modern civilization every storm season. And still, lightning remains deeply personal. Every year, people are injured or killed by strikes, often unexpectedly, far from dramatic storm scenes. Lightning can travel through ground, water, metal, and even the air around a person. It can strike miles away from rainfall, turning clear skies into danger zones. Survivors of lightning strikes often describe profound changes: memory loss, altered senses, chronic pain, or a lasting sense of connection to the event. To be touched by lightning is to be permanently changed, physically and psychologically. As we move toward the end of this journey, one truth becomes clear. Lightning is not simply weather. It is energy made visible. It is the planet releasing tension, balancing forces that would otherwise tear the atmosphere apart. Every bolt represents a moment where nature resolves an imbalance, violently, brilliantly, and without hesitation. In a world increasingly shaped by human influence, lightning remains one of the few forces that operates entirely on its own terms. Climate change is altering storm patterns, increasing the frequency and intensity of lightning in some regions. As temperatures rise, so does atmospheric instability, creating conditions where lightning may become even more common. The future sky may be brighter, louder, and more unpredictable than ever before. And yet, despite all our instruments, satellites, and models, lightning still surprises us. It forks in unexpected directions. It strikes where no one expects it. It reminds us that the atmosphere is alive with motion and power, constantly shifting above our heads. Each flash is a reminder that Earth is not a passive world, but an active, restless system. When the storm finally passes, silence returns. The air smells sharp and clean. The sky clears, and somewhere in the distance, the last echo of thunder fades away. But the energy that created the lightning has not vanished. It has simply moved on, continuing its endless cycle through clouds, oceans, forests, and skies. Lightning is not a moment. It is a process, a signal that the planet is alive, dynamic, and far more powerful than we often remember. And as long as clouds rise and air flows and heat moves across the Earth, lightning will continue to write its brilliant signatures across the sky, brief, unforgettable reminders of the wild energy that shapes our world.